Just a short overview of the talk today. So first I'll describe some proteins and text and NLP. So, and I would like to thank Alex for the introduction. So I may skip some slides I prepared. Then I'll talk about deep language models, so specifically on BERT and transfer learning, and our work, which we call this tool ProteinBERT. And if I have a few more minutes, I'll talk about another work that we are currently working on, which is a federated BERT. So I will skip on the introduction of what are proteins, and I'll refer to the previous talk. So Alex talked about the relationship between the sequence and the structure, okay? But there is also a relationship between the sequence and the function, and this is where I want to focus today. So just to give you an intuition, so with the number of sequences, protein sequences that are found, it grows exponentially with the year. So you can see over the year it goes to so the number of sequences are over 3 billion already, and the sequence of protein can be thought as similar to text. Why? Because in text, in sentences, we can have an annotation of the token of different words. So for example, I can have a word and then I can ask whether it's a noun or whether it's a verb, or I can ask whether it's a male or a female, or it's a number or a date. Maybe it's describing something else. And I can also have some global annotation on a sentence, whether it's a positive or negative sentiment. What is the topic of the document? What is the language of the text? Okay, so we can have also global annotation, and similar also for proteins. Okay, so I can ask for individual amino acid, whether it's positively or negatively charged, or what is the amount of charge, whether it has a phosphorylation site. But it can also have global annotation of a protein. What is a subcellular location of this protein? What organism is it coming from, or what is the stability of these proteins? So we can, when you think of text, so we can have some intuition of what are the tokens. So we can talk about letters, which combine to words, combine to sub-sentences, sentences, paragraph, and the complete text. And in proteins, it's not very obvious how to split the whole sequence. So the alphabet is also a little bit similar. Okay, so in the text we have, depending on the language, but 20 something letters, and in the proteins world we have 20 letters. So classical approach for protein sequences use simple NLP method like bag of words. Okay, so I'm just counting number of words or number of amino acid that each sequence has, and then representing each sequence or each protein as a fixed length of features. So we can also go into a higher dimension, so not only is individual amino acid, but also n-grams, etc. Beyond bag of words, there are also embedding methods like word2vec that was also used for protein sequences. But on the other hand, proteins are not natural language. Okay, so natural language can be understood. Okay, it's something that we use to communicate. But we can't speak or read or write a protein sequences. They are not clear what the meaning of words or sentences. The proteins vary in length. Okay, so English sentences are, let's say, maybe 20 words, maybe 500 characters, but protein sequences can be even 40,000 characters or amino acid, but the variety of length, so it's from 10 to 10 of thousands characters. And moreover, we can invent words, okay, so that's how people do, but it's much harder to invent protein sequences, okay, because it is there are physical and chemical constraints. Okay, so not every sequence of proteins of amino acids is possible. So language model had made a lot of progress and a lot of advances in the last years, and one of them used MLM method, which is a masking language model, where you take a text, then you mask, so you remove some of the words randomly, and then train a model that can predict or recapture the words that were masked. For example, if I give the model a sentence with a missing word, okay, I am blank an ice cream, the model should predict I'm eating an ice cream. Maybe there is another option like I'm licking an ice cream, maybe with a lower probability, but other words, okay, are not possible, okay? So it should get a 0 probability I'm running an ice cream, okay? And the way the model are trained is we don't need the label data, okay? We take text data, we randomly mask different words, so we take one sentence, for example, I'm eating an ice cream, and every time I mask another word, and I give it to the model. Why is it useful? Because predicting a missing word requires a deep understanding of the sentence, okay? It depends on the location in the sentence, it depends on the surrounding word, it depends on whether it's a past or a future sentence, and more. So the order of the words, of course, is also important, and this is what is called unsupervised or self-supervised learning, okay? Because it doesn't need a manual annotation of the text. How can it help us? Because we are not interested in predicting the missing word because we already have them, right? But it's very useful because it's used as a pre-training step, meaning that first we learn to recapture the missing word, and then we can take the model that we pre-train and train it on specific tasks that interest us. For example, if I want to get a text and predict what is the topic of the document, then I can just fine-tune the model in order to do this task. So here is an example of how pre-training models help us. You can see that if we don't use pre-training, okay, so this is the blue line, the performance of the model are much worse than if we use a pre-trained model. So it was already shown that pre-training, when you use a bigger pre-trained model, it usually works better, and even with small data sets. So that was just a short introduction, but what we did, it's a tool called ProteinBERT. It's a self-supervised protein language model. So we wanted to use the same approach that we used for NLP, for natural language processing, and use it for PLP, okay, protein language processing. And use self-supervised on large amount of protein sequences in order to pre-train the model, and then use it to train for specific tasks. So this is a general recipe for our protein language model. This is what people have done, sorry. It take existing architecture of a model, for example, BERT, train it on protein sequences, and then fine-tune it for different tasks. And here are some examples of other work that were done, but we did something which is different, okay? And it's different in multiple ways. So first one, we used as the input, global and local annotation. The local annotation used in the model are the input, the sequence itself, okay? And the global annotation we used or Go annotation. So Go annotation are annotation that we know about the proteins, okay? So for example, I can know what is a cellular location, what is a molecular function, and what is a biological function of the protein. So the input of the sequence was input as is. The global annotation were added to the model as a one-hot encoding. So we used about 9,000 different Go annotation. We look only on common annotations. We used linear attention, okay, which reduced the number of parameters dramatically, because usually in BERT you use quadratic attentions. One more thing, instead of MLM, which is masking individual amino acid, what we did, we replaced a different amino acid with some probability. So every amino acid had a 5% probability to be replaced with another one. And then the model had to do two things. So first of all, find the amino acid that was replaced. And second one was to predict what was the original amino acid. And same for the annotation. So with probability of 25%, we remove the annotation. And the probability of 0.01, I think, we add an artificial, a wrong annotation, okay? And the model, again, had to find which annotation was right or wrong. So this led us to a very relatively small model, okay, with only 60 million parameters. And this is compared to other models, okay, which used 38 or over 100 and 300 billion parameters. So the data set we used, so we used over 100 million protein sequences from UniRef90, meaning that we remove sequences that had a high similar to other sequences, about 9,000 Go annotation. Only a small fraction of the proteins had any annotation, okay? So only about 43 million proteins had Go annotation. And then, so we trained it on a single GPU was enough for about 3 weeks. So you can see here the performance of how the performance changed for different number of iteration or number of sequences that was trained. So for recapturing the sequence, more sequences help to increase the performance. But for the annotation, for Go annotation, it converged very fast. And okay, so that was a pre-training test, and then we use it. We used fine-tuning for specific tasks. So for specific tasks, we used in different tasks for local annotation, global annotation like remote homology, continuous annotation, for example, protein stability, also binary, whether a protein has a signal peptide or not, and also categorical annotation. So here is only a few examples. So in the row you can see different models. In the columns are different tasks. And marked in red are the ProteinBERT, which is our model. So you can see that the performance of our model are very similar to other models. For some tasks, it outperforms. For other tasks, it's similar to the other model. But what is interesting is that our model is very small relatively to the other model. And the advantage is also in doing the training, also the fine-tuning, and also doing the prediction phase. Okay, so it runs much faster. Okay, I'll skip on those. And I'll summarize that, and then I want to say a few more words on a current work. Okay, so pre-training works, and protein are, on one hand, are similar to text, and we can use NLP method for protein sequences. On the other hand, they are different, and this difference can be used also. So if we understand what are the differences, we can use that in order to train better models. Unsupervised learning or semi-supervised learning or self-supervised learning can make use of a large amount of data. And if you have a good model, then you don't need thousands of GPUs or infinite resources. And we showed that our model, so ProteinBERT, is very useful for a task where we have only a small data set for the fine-tuning. So the code and the paper are available. And these are just a few examples of methods that used our ProteinBERT. And okay, so I just want to mention in a few slides our next step. So we want to use NLP method, not for text, not for proteins, but now for clinical data. You can think of clinical data also as a sequence of event or sequence of information. Okay, so for example, a patient came to the hospital, then he had this diagnosis and another diagnosis, and then he took a lab test, and then he was discharged and readmitted again to the clinic. Okay, so you can represent a sequence of event as a text, and use BERT architecture for learning or for representing medical or clinical concepts. So there are several works. So for example, we use the BERT, okay, BERT, but we wanted to use it in a federated learning. Why federated learning? Because clinical data is very sensitive. We cannot centralize it in a central location. And these are our unpublished results. Okay, so for a specific task, the task is called the next visit prediction. So we want to predict what is a diagnosis that a patient will have in the next visit during previous diagnosis and previous clinical visit. So in the blue bar, you can see a non-federated learning where you have all the data centralized. Okay, these are the average precision. In orange, you can see the federated learning approach, which achieved almost the same performance of the non-federated or the centralized learning. And the green one are performance when you train a model for every location, for every, let's say, clinic, use its own data and its own model. So with that, I would like to thank the part of the group member that used of these two works. So Dan Offer, Nadav Bandes, Jan Peleg, and Michal Lineal for the ProteinBERT. Specifically, I would like to thank Dan Offer, who also made most of the slides, and Ophir Ben Shoam, who worked on the clinical BERT. And with that, I would like to have some questions. Thank you. So we didn't use that, but you can. Okay, so it's like a model representing. You can use it to embed proteins, and then you can use it for any task you want. So, but we didn't use it for designing proteins.
I understand that you mentioned that you've eliminated the need for self-attention.
Right.
So what kind of another mechanism did you use to implement the transformer?
So we used the global attention. Okay, global attention. We have one attention. Every position relate to that.
Can you please elaborate a bit? I'm not sure I understand.
Maybe I'll do it offline.
Okay.